In the last several videos, we have been looking at the geometric product. But why should we care about it? What can it actually do? In this video, we will finally start to answer these questions. This video is a part of From Zero to Geo, a series where we formulate geometric algebra, an incredibly powerful branch of mathematics, from the ground up. Before we get into the main topic of the video, I need to give a bit of a warning. Up until this point in the series, we have been building the foundations of geometric algebra. This involves things like vectors, multivectors, and the definition of the geometric product. To introduce these ideas, I have been appealing to basic mathematical intuition, built from our experience with elementary geometry and algebra, since there was nothing else to use. The issue is that it's not actually good to think about geometric algebra in terms of elementary geometry and algebra. Now that we have used those things as a crutch to get the foundations down, we need to cast off that crutch and develop new ideas based on our new foundation. But a massive paradigm shift like this takes time. It is going to take several videos for us to really see and understand how these new ideas actually work. In the meantime, we won't really be able to give any precise definitions. After these videos, we will then pick up the pieces and make all of these new ideas much more formal and precise. So, I guess my main warning is that the concepts in the next several videos are going to be very different than what we have seen so far, and that we won't even be formally defining them for quite a while. Anyway, with that out of the way, let's get into the topic of this video. In the last video, I left you with an exercise. If you need a refresher, here it is again. Given three vectors, we can calculate their geometric product and draw it graphically alongside the original vectors. I asked you to repeat this process with all of these sets of three vectors and look for any geometric patterns. If you haven't tried this yet, I would suggest pausing the video now and doing it, since the answers lead to the main topic of this video. So, I'll just show the answers here. Here are all of the products algebraically. Before we look at them graphically, let's put subscripts on all of the variables to keep track of them. Now, here are all of the vectors drawn graphically. The thing I wanted you to notice is that in each set of four vectors, the angle between v and w is the same as the angle between u and uvw. For example, in the first case, the angle between v and w is a right angle, and the angle between u and uvw is also a right angle. In most of these cases, I purposely made the angle small to make this easier to recognize, but even in the last case, where the angle is much larger, you can see that the angle between v and w is equal to the angle between u and uvw. But how do we know that this is always true? It was true in all the cases we looked at, but to know that it's always true, we need a proof. You may have tried to prove this already while doing the exercise, but if you haven't, try to do it for yourself first. See if you can find a reason that the angle between u and uvw is equal to the angle between v and w. First, let's look at a simpler situation. Consider the case where u equals v. In this case, we are trying to prove that the angle between v and vvw is equal to the angle between v and w. So all we have to prove is that vvw points in the direction of w. And this is directly true because v squared is a positive scalar, so v squared w is just a scaled version of w. In fact, this argument works as long as u points in the same direction as v. Because u and v are pointing in the same direction, their product is a scalar, so uvw is still just a scaled version of w. But now what about the general case, where u and v point in different directions? For the moment, let's forget about u and just focus on the product of v and w. We've seen in previous videos that it's the sum of a scalar and a bivector. Scalars aren't affected by rotations, and in two dimensions, bivectors aren't either. This means that if we rotate v and w by the same amount, their product stays the same. So given any vectors v' and w' that are the rotated versions of v and w, their product is equal to the product of v and w. Bringing u back into the picture, we can rotate such that v' lines up with u. Then, uvw is equal to uv''w'. U and v' now point in the same direction, so we can use our previous argument. The product of u and v prime is a scalar, so u v prime w prime is a vector pointing in the direction of w prime. We constructed w prime so that the angle between it and u is the same as the angle between v and w, so in the end, the angle between u and uvw is in fact equal to the angle between v and w. Another thing you might be wondering about is the magnitude of uvw. Let's try to figure this out too. First, let's consider the case where u, v, and w are all unit vectors. When going through the previous argument, v prime and w prime will be unit vectors as well. Since u and v prime are both unit vectors pointing in the same direction, their product is 1, and the final result, w prime, has a magnitude of 1 too. So, when u, v, and w all have a magnitude of 1, their product does as well. For arbitrary vectors, we can employ an algebraic trick. We can multiply and divide each vector by its magnitude. Since scalars commute with all multivectors, we can then pull out the magnitude of each vector. The resulting vectors on the right are now the normalized versions of the original vectors, so they are all unit vectors. By what we just saw, this means that their product is a unit vector as well. Taking the magnitude of both sides, we see that the magnitude of the product of three vectors is simply the product of their magnitudes. So here's the final description of the product of three two-dimensional vectors. The angle from u to uvw is equal to the angle from v to w, and the magnitude of uvw is equal to the product of the magnitudes of u, v, and w. Now there is one important thing I need to say. This interpretation of the product of three vectors only works in 2 dimensions. Even in 3 dimensions, the product of three vectors doesn't have to be a vector, so the whole argument we just made breaks down. But in 2 dimensions, this description of the product of three vectors is correct, and it will be useful for us moving forward. So what use is any of this? Well, let's look at a particular situation where we can use this. Let's say we wanted to rotate this vector by 30 degrees. How can we calculate this? Well, if we can find 2 other vectors v and w that have an angle of 30 degrees between them, upon multiplying u, v, and w, the results will be precisely the rotated vector, but with a different magnitude. Since rotations shouldn't change magnitude, we don't really want this scaling. We can fix this by normalizing v and w before calculating the product. If v and w are normalized, the magnitude of uvw will be equal to the magnitude of u, which is what we wanted. Here, let's do an exercise to get better acquainted with this process. Here are 3 vectors. For each vector, I want you to rotate it by 3 different angles. The first angle is 90 degrees, the second angle is 45 degrees, and the third angle is the angle between E1 plus 5E2 and E2. So yes, I want you to calculate 9 different rotations. Make sure you get the magnitudes right. Again, rotations don't change magnitude, so you need to make sure that you normalize where you need to ensure that this is the case. Please pause the video and calculate all of these rotations. Let's start with the first vector and the first angle. To rotate a vector by 90 degrees, we need to find 2 unit vectors that are at a right angle. The easiest vectors to pick are E1 and E2. Then we just need to calculate this product to perform the rotation. The next angle is 45 degrees. The angle between E1 and E1 plus E2 is 45 degrees, so let's use these 2 vectors. But wait! E1 plus E2 is not a unit vector. So if we tried to rotate with these vectors, we would end up scaling the result. We don't want that. We can fix this by normalizing E1 plus E2. Its magnitude is the square root of 2, so we just need to divide E1 plus E2 by the square root of 2. With this, we can rotate by calculating the product as before. For the third angle, we aren't given the angle directly, but that doesn't matter. We just need to multiply our starting vector by these 2 vectors. But again, we need to normalize the vectors first. Once we have done this, we can calculate the product. Let's now move on to the second vector. This time, we can take a bit of a shortcut. Last time, we already calculated the product VW for each of the three angles. We can reuse that calculation when performing the new rotations. So we just need to multiply the vector by these three different values for VW. And for the third vector, we can do the same thing. We just need to multiply the vector by VW in each case. This problem has shown us that we don't really need to think of rotations in terms of a full product of three vectors. We can rotate any vector by 90 degrees by multiplying it by e12, we can rotate any vector by 45 degrees by multiplying it by 1 plus e12 divided by the square root of 2, and we can rotate any vector by whatever that last angle was by multiplying it by 5 plus e12 divided by the square root of 26. In a sense, these multivectors represent the rotation itself, which we can then apply to a vector by multiplying the vector by the multivector. This point is important, so I am going to repeat it more clearly. Some multivectors represent geometric transformations rather than geometric objects. The way that we represent geometric transformations using multivectors is the fundamental idea in geometric algebra. While at the current moment we have only seen how this works with two-dimensional rotations, we will come across many other situations where this idea of representing transformations with multivectors comes up. Understanding the dual object transformation nature of multivectors is going to be essential for us moving forward. Because the product of two unit vectors represents a rotation, let's give it a new name. Since these multivectors represent rotations, we'll call them rotors. Recall that way back in Chapter 1, I said that the two main properties of a vector are its length and its orientation. We figured out how to change the length pretty quickly by using scalar multiplication, but we were never able to figure out how to change the orientation of a vector. Well, we have finally stumbled on the answer without even trying. We can rotate vectors by using rotors. Given a vector and a rotor, we can calculate the rotation of the vector by that rotor by just multiplying them. Again, it's important to note that this way of applying rotors only works in two dimensions, although there is surprisingly little that changes in higher dimensions. Now, there is one issue with this way of rotating vectors that you may have noticed. Often, we want to rotate by a given angle without having to find two other vectors with this angle between them. Is there a better way to make rotors than multiplying vectors? We'll answer this question in the next video.